Hi, so for today we're going to talk about definite integrals and we're going to do some examples, then study the properties of definite integrals, some properties of the definite integrals. Well, let's start. So definite integral is actually different from indefinite in a sense that definite integrals has its what we call limits. So as you can see here, we have A and B. And this is actually the limits. So in order for us to read this, it is read as the integral of f of x dx evaluated from A to B. Okay, this A and B can be any number. Okay, it can be any constants. So definite integrals always result into a constant. Okay, so unlike, for example, we have indefinite integral here. So this is an example of an indefinite integral wherein indefinite, wherein we don't have any limits here. Okay, we don't have any A and B's here. And we know that if we integrate this, we should get x squared over 2 plus a certain constant c. But in evaluating definite integrals, we should be getting a constant value, any number, okay? Not this expression anymore, okay? So, if, in order for us to evaluate a definite integrals, so we have to use this formula. So this is simply equal to the integral of f of x dx evaluated from a to b is simply equal to the function of b minus f of a. So what does that mean? So whatever the values of the a and b here, we're going to substitute it. Take note from the upper integral or upper limit minus the function evaluated at the lower limit. Okay? So f of b minus f of a, this will result to a constant value, not any more expressions, because we are talking about definite here. From the word itself, definite, the result should always be a constant number. Okay? So here are some properties of definite integrals. This might be useful for some applications of definite integrals. So we have property number one, we have the integral of f of x dx evaluated from a to b. That is only equivalent to the negative of the integral of f of x dx from b to a. If we switch the limits here, okay, such that this would be from b to a, okay, we should put negative sign here. So in these two are equal. Okay, for number two, the integral of f of x dx evaluate from a to a. If we have the same limits, okay, the integral, no matter how complex the f of x, if they have the same limits, then we are not integrating anything. Okay, so that should be equal to 0. So in other words, if the upper limit is the same as is equal to the lower limit, whatever f of x you have, the result of that definite integral would always be equal to 0. Okay? So, for number 3, we have the integral of c f of x dx where c is any constant. So, using the property, we can actually factor out the constant, this c, and evaluate the integral of f of x dx from a to b. Okay? So, these are the three properties. For number 4, we have the addition and subtraction property. So, if we have two functions, we're going to integrate it separated by an addition or subtraction. So, we can decompose it in this equation. Okay, just like the properties of indefinite integral, wherein if you have two functions uh, separated by plus or minus sign, we can actually what do you call this? Decompose them into two single integral. So such as this. So still this the same limits from a to b, from a to b. Okay. For the fifth property we have here, evaluate the integral of f of x dx from a to b, and that is equivalent to the integral of f of x dx from a to c plus the integral of f of x dx from c to b. Okay, here, the c here can be any number, okay, evaluated from, well, of course, in most cases, this c is actually in between a and b, but that is not always the case. Okay, we're in, there is a case that this c is not in between the numbers a and b. So for example, our value of A here is 0, and our value of B here is, let's say, 4. So we can decompose the integral, let's say, from 0 to 2, okay? And here from 2 to 4. Okay? So for example here also I have from negative 1 to 1, okay, f of x dx. So what can I do is first is integrate this from negative 1 to 0 of f of x dx plus the integral of the 0 to 1 of f of x dx. So you can use that property in some applications, okay, or in some cases. So for number 6, we have the integral again of f of x dx evaluated from a to b. And that is only the same if we evaluate the integral in terms of t. Here, we evaluate our variable is in terms of t. So that's why we have dt here. Here, our variable is in terms of x. So if the function is the same, but the variables are not the same, and it's a same function, but don't have different that have different variables, so it is still equal. So for example, if I'm going to evaluate the f of x, let's say that is x dx evaluated from a to b, that is only the same if I'm going to evaluate, okay, the t dt. So as you can see here, what we did is we use an x variable, and here we use a t variable. So given that a and b are the same for each integral, the resulting definite integral should always be equal. Okay? So let's try to solve some problems. Yes. So, so for number 1, we have to evaluate. It says the integral of x. What is that? X dx. Okay, let's start with a simple one. X dx from 0 to 3. Alright, the process is still the same. Okay, the process is really the same. How are we going to integrate x dx? Okay, without these limits. So let's try to integrate that. So what's the integration of x dx? So that would become x squared over 2. Okay, so the difference is we say that if we evaluate definite integral, this should not be our answer. It should yield to a constant number. So we have the limits from 0 to 3. So we have the symbol to evaluate it from 0 to 3. Okay? So what did we say a while ago? From our formula, we have f of b minus f of a. The definite integral is evaluating this. So in this case, our b is 3 and our a is 0. So simply substitute the values of b, which is 3, on the function, minus f of a, which is 0. We're going to substitute it here. So what will happen is that we have 3 squared over 2 minus the lower limit, because f of a is 0 squared, or 0, yeah, 0 squared over 2. This is actually 0, okay? That is 0. So 3 squared over 2, 3 squared is 9. So divided by 2, this should be our answer if you're going to get the integral of x dx evaluated from 0 to 3. Okay, pretty much easy, right? So the only difference is that if we evaluate definite integrals, it should yield to a constant value. So for number two, we have the integral of the hyperbolic tangent, okay, of 5x cubed minus 4x dx, okay, evaluated from 5 to 5. Okay, so looking at the properties of what we have discussed a while ago, this should yield to what? To what number? 0. Okay, why? Because we have done no integration in this. Okay, so we evaluated this from 5 to 5. So A and B has the same or equal values, and by the property we have discussed a while ago, if we have two limits that are equal in our integral here, the value of that integral should be always equal to 0. So hence, our answer here should be equal to 0. So for number 3, so again, for number 3, we try the integral of 4x cubed minus 6x minus 5 dx evaluated from -1 to 2. Okay, again, this is a simple integration, okay, by power formula. So we have 4x raised to 4 over 4 minus 6x squared over 2 minus 5x evaluated from -1 to 2. So before we evaluate the definite integrals or the limits here, so let's try to simplify this. So 4's will cancel. 6 divided by 2 will be 3. So we have x raised to 4 minus 3x squared minus 5x evaluated from -1 to 2. So what happens next? We can therefore now substitute. So be careful. 2 raised to 4 minus 3, 2 squared minus 5 times 2 minus, this is the minus sign, minus of the -1 raised to 4 minus 3 times -1 squared minus 5 times -1. Okay? So 2 raised to 4 is, I believe, that is 16. Minus 4 times 3, that is 12. Minus 10. Minus, okay, -1 raised to 4. This will be positive 1. Okay? -1 raised to squared. Positive 1 again. Multiplied by -3, we have minus 3. -5 times -1 is plus 5. So if we're going to evaluate that, 16 minus 12, that is 4. 4 minus 10, that is -6. Minus 1 minus 3, -4. Or -2 plus 5. So that would be equal to 3. So in this case, -6 minus 3, that should be equal to -9. So this is our result for our definite integral example number 3. Okay, pretty much easy, right? So if the integral yields with some certain fractions, then you should be able to actually perform addition and subtraction of fractions. Okay, because we are not allowed to use the calculators here. So for number 4, or if you wish to use a calculator, you're taking a board exam, you can use it. Okay, Viola, you have already the answer. But this is the long method of actually solving the definite integral. Okay, let's try another example. So for number 4, we have the integral of 3x squared minus 1 over x squared dx evaluated from 1 to 2. Okay, so what we can do here is simply we can split, okay, this integral into 2. So we have the integral from 1 to 2 of 3x squared over x squared minus the integral from 1 to 2 of 1 over x squared dx. Okay, from here, we can see that these two will cancel. Okay, we have also a dx here. I forgot to write. So we can factor out 3 outside of the integral so that it leaves us this integral minus uh, the integral of 1 over x squared evaluated from 1 to 2 at dx. So we can integrate this simply. We have 3. Okay, we have x evaluated from 1 to 2 minus, okay, so if we find the integral of this should look like this, okay. So we have -2 plus 1. So what will happen here? We have x raised to -1 over -1. And -1 times the negative here, it would yield to positive. And what will happen if we wish to get this back on the denominator? So 1 over x. So we have what? 1 over x, okay, from 1 to 2. So simply, again, substitute it. So we have 3, 2 minus 1 because the limits are 2 and 1. The b is 2 and the 1 is a. Okay, plus, okay, 1 half, okay, minus, okay, 1 over 1 is simply 1. Okay, so we have 3 times 2 minus 1, that is simply equal to 3, plus 1 half minus 1. And if we perform this should be equal to, let's perform this first. So we have 1 half minus 1, that is negative 1 half. So if we have this, 6 minus 1, that is 5 halves. So our answer should be 5 halves for this example. Okay, so let's try another one. So this time let's try number 5. Okay, integral from 0 to pi over 2 of x squared sine of x dx. Okay, so in evaluating definite integral, we will recall our integration techniques, okay, for indefinite integral. So probably we're also the techniques used for indefinite integral are the same techniques also we are going to use the definite integral. So in this case, x squared sine of x, we should be using IBP. And what do we here? We choose the value of u. And the priority of choosing u here is x squared. Get the derivative, that is 2x dx. So what left is the dv. If you haven't watched my IBP, please watch it so that you can understand in the process what I'm telling here. So dv, we have sine x dx, and if we integrate this, we should get v, and that is equivalent to negative cosine of x. Okay, so what are we going to do? The formula is uv minus the v du. That's still the same. So we have uv. Okay, we have x squared minus times cosine, negative cosine of x. Well, of course, the difference here is that uv, we also have to evaluate the limits from 0 to pi over 2 minus the integral of 0 to pi over 2 of the v du. The v du is still a negative cosine of x. Du is 2x dx. So first, we should evaluate this first, okay? So what will happen here is that we have x squared pi over 2 squared minus, okay, the cosine of x, okay, cosine of the a or b, okay, minus, okay, the 0 squared. Well, of course, 0 squared, because the lower limit is 0, we substitute to 0. So any number multiplied by 0 should be 0. So this minus term will become 0. Okay? And of course, here on this side, we can actually factor out the negative sign. So that would become positive. We can factor out 2. So we have plus 2, the integral of 0 to pi over 2. We have now cosine of x. Of course, we should write first x cosine of x. So because we leave an x here. So x cosine of x dx. So how do we evaluate this? Pi squared over 2 is pi squared over 4. But the cosine of pi over 2 or the cosine of 90 is usually equal to, or in fact equal to 0. So 0, any number multiplied by 0. So simply this whole term will now be equal to 0. And then we're going to integrate again from 0 to pi over 2 this x cosine of x dx. Again, this is integration by parts. We should choose u as x, and du, if we evaluate, oops, I'm sorry. Okay, u is equals to x, and du should be equal to dx. Okay, and what's next? We have dv as cosine of x dx. Okay, and if we integrate that, that should be equal to sine of x. So, again, applying the formula. So, this should be our formula. We have 2 outside and we're going to evaluate that. That should be uv minus vdu still. Okay? So, 2 multiplied by the uv, we have uv. U is x, v is sine of x. Well, of course, still evaluated from 0 to pi over 2. Don't forget that always. Minus the integral from 0 to pi over 2 of the v du. So we have v du as sine of x du is equal simply to dx. So first, we evaluate this. Okay, so we have 2 pi over 2 sine of pi over 2. Okay, minus, of course, if x is 0 here, so this whole equation on the evaluated from a should be 0. Okay, so sine pi over 2, sine 90 is actually sine pi over 2 is 1. Okay, minus 0. Okay, and minus, plus, how are we going to integrate this? Okay, the integral of sine of x dx is negative cosine of x. Okay, evaluated from 0 to pi over 2. Okay, so what will happen? Let's simplify. We have 2 here. Pi over 2 times 1 is simply pi over 2. Okay, minus 0. Okay, so minus, let's evaluate this. The negative cosine of pi over 2 minus of the negative of cosine of 0. Okay? So we have 2 pi over 2. Okay? So this is another parenthesis here. Okay? So negative cosine pi over 2, cosine of pi over 2 is simply 0. Okay? And cosine of 0 is simply 1. So we have negative, so that should be a negative 1. And we have minus here, that should be positive 1. And we have a minus here, that should be minus 1. Okay? So, simply, we have 2 pi over 2 minus 2. Okay? So, what will happen here is our answer is actually pi minus 2. So, this should be our answer for our definite integral of the x squared sine of x evaluated from 0 to pi over 2. Okay, let's proceed now to our next example. Okay, so what is our next example? If I'm not mistaken, we have here uh, for number 6, we have the integral of 10x squared plus 10 dx evaluated from 0 to 2. This is another easy example. So what will happen? We have 10x cubed over 3. So plus a 10x evaluated from 0 to 2. Okay, so we have 10 cubed of 10 over 3 over 2 times 2 cube plus 10 times 2, okay, minus, well, of course, this is 0, so x cube, 0 cube over 3 is 0, plus 10 times 0 is still 0, so this should be simply equal minus 2, 0. So we have 2 cube is 8, 80 over 3 plus 20. Okay, so we have what? 80 plus 60 over 3, that is 140 over 3. So can we still simplify this? No. So this is the answer for our uh, definite integral here. Okay, pretty much easy, right? So let's try another one. Some easy examples. So integral from 0 to 2 of t squared plus 1 dt. So in this case, we have used the t as a variable. Okay? It makes no difference if we get the integral from 0 to 2 of x squared plus 1 of dx. Okay? So let's try to solve. So evaluate this. So we have a t cubed over 3 plus t evaluated from 0 to 2. So we have now 2 cubed over 3 plus 2 minus, if we substitute 0 here, 0 over 3 is 0 plus 0 is minus of 0. So simply we have 8 over 3 plus 2. So we have 8 plus 6 over 3. So 14 over 3 is our answer. So let's check if we have the same answers here. So if evaluate the integral of this should be x cubed over 3 plus simply x evaluated from 0 to 2. And as we can see here, the only change that happened here is the change in variable. Okay, but it would still yield to the same answer. So we have 2 cubed over 3 plus 2 minus 0. So we have 8 over 3 plus 2. So that is 6 plus 8. So 14 over 3. Still the same answer. Okay, and that's all for now for definite integral. I hope you have learned something in watching my videos. Thank you so much for watching my videos about definite integrals, and hope to see you soon on another next video, or on our next videos about calculus. So thank you so much for listening, and God bless you.